about connectivity-based clustering. So what I want to teach you today is the limitations of K-means and soft clustering with Gaussian mixture models, which have been the topic of last week's lectures. Then I will introduce you the idea of representing data using a graph. In particular, I call it an empirical graph. And then we will see how representing data as a graph allows us to define notions of connectivity between nodes. And we will use these notions of connectivity to cluster data points. And as often, there are different design choices for how to define connectivity or what we mean by connectivity. And I will show that two specific definitions or notions of connectivity lead to two very popular and powerful clustering methods, which are called spectral clustering and DBSCAN, which refers to density-based clustering. We will not go into very much detail of these methods and their analysis. You will also not need them for the student project. So the student projects don't require you to cluster the data points, but I will introduce you the key concepts so that you are somewhat familiar with clustering methods. When you then want to deepen your knowledge, there are plenty of follow-up courses, in particular then also on the master level courses that go in depth into the analysis and implementation of clustering algorithms. But first things first, so what are three components or three main components of machine learning? Yeah, this is now really fast on the chat. We have already 4 answers, but I want to see at least 10. Yeah, this is the main goal for me as a teacher for this course, that you answer this question in the middle of the night when you just wake up. So 3 components of the machine learning is data, a model, and a loss. So let's now look at K-means hard clustering. So what kind of data did we use there? How did we represent data in K-means clustering? In what form is K-means clustering using data? Yeah, using feature vectors. Very good. Let me just add this here, fill it out. So feature vectors. What is the model in K-means? What kind of model did we use? The model is always a set of functions that map features to some label. What was the label, or what was the meaning of the label of a data point in K-means clustering or in clustering problems in general? What is the label value representing of a data point in a clustering application? The cluster index. So a label, so we have a feature vector, but we also have a label, which is the cluster assignment. So formally, we also have labels in clustering, but what is special about clustering methods or K-means is they don't need to know the true label value, the true cluster assignment for any data point. So we only need the feature vector, but clustering methods try to predict the cluster assignment. So we still have a function, age of x, that reads in the feature vector of a data point and outputs a cluster assignment, which is a predicted label. So a model, in this course, I refer by the term model to a set of such functions. So what type of functions does K-means use? So how does K-means restrict this assignment of a feature vector to a cluster or cluster index? It does not allow for any such assignments. It prefers certain cluster assignments. Yes, it uses the Euclidean distance to look at the distances or how the cluster indices are distributed over distant data points. And in particular, K-means uses such maps that read in the feature and output a cluster assignment, so a predictor map, such that the cluster index for data points which have feature vectors that have a small Euclidean distance have the same cluster index. So that's the model, the underlying model of Kmeans clustering. So let's write it out. Map data points with close by feature vectors to same cluster index. And then you can find different types of such functions, age that map a feature vector X to a cluster index that conform with this model or assumption. So that's used by Kmeans. What is the loss function? How do we measure how good a clustering has been? So Kmeans method reads in the feature vectors of data points and outputs a predicted cluster index or cluster assignment. But then we need to measure somehow how good are we doing. So in machine learning, we always need a loss measure. What was the loss measure that we used that is used in Kmeans? I've seen it already before in chat. We use a distance to a cluster mean. So we use this is called then the clustering error. This is the average squared distance or Euclidean distance between data points or feature vectors of data points, between feature vectors and nearest cluster mean. Okay, that's just one example or one instance of a loss function. We used also loss functions for linear regression, where the loss function was the squared error, but here we use the clustering error. So that's another loss function. So now let's look at the other clustering algorithm we looked at last week, which was a soft clustering algorithm based on Gaussian mixture models. And already in the name, we can identify the model. The model for this soft clustering algorithm has been Gaussian mixture model. So we assume the data points are realizations of mixture of Gaussian distributions, or let's call it Gaussians. So that's a probabilistic model, but in the end, it's again corresponds to a map that reads in a feature vector and outputs. What is the output of this predictor map for soft clustering? Does it output a cluster index like in Kmeans? What is the output of the soft clustering algorithm that I discussed last week? It's kind of a degree of belonging. So the output is a degree of data point belonging to a cluster. But we can interpret this also. So this is the be interpreted within a Gaussian mixture model as a probability of data point drawn from cluster distribution. Remember, in Gaussian mixture models, we represent a cluster by a Gaussian distribution, and the output of this predictor map is can be interpreted as the probability that the data point with feature vector X has been drawn from a particular cluster distribution. So remember, the output is not a single number, but actually we output the degrees of data point belonging to all different clusters. So these are probabilities drawn from cluster distributions. Yes, and the loss function we had similar to Kmeans, we had a clustering error, but we now called it a soft clustering error because it takes into account that the data point belongs to several different clusters with different degrees of belonging, which take on values between 0 and 1. So we can also interpret soft clustering algorithms within this three-component picture. Okay, so let's look again at an example application. For example, we want to segment an image. So we take one image and we cut it into small rectangular pieces or patches, and each patch is a data point. And then we compute two features for each data point, the average redness and the average greenness. So we can represent each data point then in a two-dimensional plane. And now this data set is what we could feed in a clustering algorithm like Kmeans or the soft clustering algorithm. So what we got from hard clustering was a cluster assignment that follows basically spheres. So K-means produced clusterings where each cluster is enclosed in a sphere, in a ball, in a symmetric ball, roughly speaking. And in contrast, in soft clustering, we obtained clusters which fit into an ellipsoid. So it's a bit more general than what K-means can do. K-means only can deliver symmetric or isotropic ellipsoids. I don't know if that's the right word. So these are symmetric ellipsoids or balls. Whereas soft clustering delivers clusters which are more, which can be stretched in some dimensions. So there was one, yeah. So these pictures here, they are just cartoons. So don't take them literally, because as pointed out, what happens with the data points outside these balls? Yeah, in hard clustering, remember, each data point is assigned exactly to one cluster. So this is not 100% correct, this picture, because in K-means, what we get is, or what K-means does, it basically, if we cluster it into two clusters, so it divides the feature space into two half spaces, which is the divider between the cluster means, and then it assigns all data points on the same side to the same cluster. So each data point is assigned to one cluster. But to get a feeling or some intuition, when you have more than two clusters, then typically the clusters are arranged like this in these spheres. So it's an approximation of the output of hard clustering, but it gives some intuition. In particular, it shows us, or it guides or helps us to understand where K-means clustering or the soft clustering algorithm fails. And it fails for non-Euclidean cluster structures. So what do I mean by non-Euclidean cluster structure? Well, let me ask you, how many clusters do you see in this data set? So in this data set constituted by these blue blobs, do you see clusters? Do you see a cluster structure there? Yeah, so many of you said two clusters. Can anybody describe the two clusters? Yeah, one very good comment. Two clusters, one inner and outer circle. And this is something that a K-means, neither K-means nor the soft clustering method based on Gaussian mixture model can do. Because just try to fit two ellipsoids such that they exactly resemble the two clusters in this outer circle and in this inner circle. So I can try it. So I have one ellipsoid, try to fit this here, make it a bit transparent. And then I have the other cluster, which is again an ellipsoid, if I use Gaussian mixture models. So I have a bit more degrees of freedom, but then you cannot only cut out the inner circle with an ellipsoid without also taking parts from the outer ellipsoid. So it simply doesn't work. But then let me ask the student who posted on the chat that there are two clusters, one inner and outer circle. How did you identify these clusters? How did you come up with this choice or guess for the clusters? Yeah, again, there's a comment, there are two rings and each ring is a cluster, but how many of you have the right intuition, but how did you come to this intuition? How would you explain this, try to make this more mathematical, precise? Yeah, they order in some unique shape, so there's some order, but what do you mean exactly with order? Then there's a very good comment. We could connect all data points with the smallest distance between them. So we could connect each data point, and this brings me exactly to the next slide. So maybe some of you have already looked at my slides that I have posted. So what maybe some of you did kind of unconsciously, so without explicitly recognizing it, when you looked at this data set, you started to make some order. You order it. Maybe we have a need or an urge to order things, to understand things, to group objects. And what we can do here, we can say, okay, we can group together these close by data points and then look at what structure then unfolds when we connect those close by data points. So if we connect this close by data points, and now maybe I change to my iPad. So let's hope this flies. Hold on a second. Yeah, I'm missing the times of giving lectures with a blackboard. So let's say we have again a data set, and each dot here represents one data point. Try to quickly redraw this. And what many of you might have done without explicitly recognizing it, so you have connected those nearest neighbors. And then just said, okay, there are two connected components. So can everybody see my sketch here? Yes, okay, thanks. So you might have connected those like this in these kiddies journals when you have paintings and there you see only the dots and you have to connect the dots. I guess it's called connect the dots. So you have connected the dots internally and then you found there are two paths. We call those connected components in graph theory. And then you could have said, okay, it seems that there are two clusters and each cluster, so this here is one cluster, call it cluster 1. Then let's use another color. And here we have cluster 2. Cluster 2. And what you have done already, you have already implemented or executed a connectivity-based clustering method. You have defined a similarity, or you have somehow introduced a notion of similar data points. So similar data points are those which are nearest to each other. And then you just have said, okay, I group together all data points that are similar and all the other all data points that are similar to each other. So this gives kind of a relation, a mathematical relation, which we can make precise using the concept of connectivities. And then all similar data points are clusters. Okay. Do you have any questions? Because this is basically the key idea behind connectivity-based clustering methods. Okay, let me show you another example. So let's say we have a data set that looks like this. And how many clusters would you spot here? Yeah, two, because also this could be already identified by Kmeans. So also Kmeans would maybe have delivered those two clusters. But also this example we can solve, or we can approach via connectivity-based clustering. So we can again say we connect the nearest data points in Euclidean space with each other. Then we get two triangles, and then we look at the connected components and identify each connected component. So this here is one, and this is the other one as cluster. And this is exactly the operational principle of spectral clustering. And spectral clustering is also versatile in the sense that you can define similar data points. So just connecting them, if they are close by in a plane, is one example. But what spectral clustering methods need as input is essentially only this edge structure. So we call these edges of a graph. And the data points are the nodes of a graph. And this is then called an empirical graph, this whole graph structure. So a node, these are the data points, some data point. And what spectral clustering method needs is just the edges between the data points. Yeah, I use the term empirical graph just to distinguish it from a general abstract graph. So there's a whole big mathematical field called graph theory, and we just use their techniques. But if we use a graph to represent a certain data set, I call it empirical graph. That's just my convention. Yeah, I use the term empirical graph to highlight that each node here, so that these nodes here are representing data points. So a data point, yeah, and this already leads me to one of the big advantages of the spectral clustering methods. This data point can be anything. This could be a feature vector, like the redness and the greenness of an image patch, but it could also be something completely different. It could be, for example, a data point could be a piece of text. So in natural language processing, we might consider data points being a text. The most minimal text is one word. So one data point could be hello. Another data point could be hi. Another data point could be moika. So we can then use similarity notions for words. So let's say we have here another data point, run, go, walk. So what do you think could be the similarity notion that I used here for these data points? Why did I connect the data point representing the word hello with the data point representing the word hi? Do you think this makes sense, this similarity, this definition for similar words that I did? Yeah, the meaning. So it seems quite natural to say the word hello is similar to hi, because the meaning is somewhat similar. When you meet somebody, you introduce yourself or you greet him or her with hello or hi or moika if you're Finnish. So they have somewhat the same meaning or the same role. And similar here for these data points, run, go, walk. They all refer to different modes of moving. So you can then use this domain specific, in this case, these are natural language processing specific similarity measures to define this empirical graph. And once you have the empirical graph, so once you are clear about which data points, or in this case, which words are similar, you draw edges between them, and then you input them to spectral clustering methods. This makes them very versatile. So you can apply spectral clustering to any kind of data points for which you have some good intuition how to consider data points similar or not. And one example of the similarity measure, which is used by Gaussian mixture models or soft clustering and Kmeans, is you look at data points represented by feature vectors like redness and greenness, and you compute the Euclidean distance between two data points. And if this Euclidean distance is small, you consider them similar. So K-means and Gaussian mixture model clustering use one special case of a similarity notion. However, we can use different, way different similarity notions. And all these different similarity notions give rise to an empirical graph. And an empirical graph we can feed in or we can input to a spectral clustering algorithm. Okay, so spectral clustering is really a cool tool, I have to say. And if you want to learn more, I can give you pointers. Just write me an email because the details of spectral clustering is well beyond the scope of this course. Our course is meant for first or second year bachelor. Spectral clustering would be a master level course if you really want to consider it in depth. But there was one very good question. Why is it called spectral clustering? And I want to briefly discuss why it's called spectral clustering. So, and this brings me to matrices. Our course assumes as a prerequisite matrix algebra. So formally, we assume every one of you to be familiar with the concepts taught in the course matrix algebra at Aalto or anywhere else. And one key concept of matrix algebra is something called eigenvalue decomposition. And the term spectrum often means nothing but the set of eigenvalues of a matrix. And I will now show you one or several matrices that we can naturally assign to a graph, an empirical graph. So consider here a data set consisting only of 4 data points. So we have 4 data points: data point 1, data point 2, data point 3, and data point 4. And somehow we came up with a similarity notion. So we found out, for example, the data points 1 and 2 mean similar words or are similar words. So we connected them by an edge. And also data point 3 and 4 are similar, so we connected them by an edge. And we can encode, so this whole thing is the empirical graph of the data set. Empirical graph of this data set of 4 data points. And then there are a few matrices that allow to work with graphs and to analyze them. One is called the adjacency matrix. So the adjacency matrix is, in the simplest case, taking values only 0 and 1. And an entry, the entry in the ith row, so this here is row number 2, corresponding to the second data point. And the jth column, so this here is column j equal 3. This corresponds to the third data point, and the entry is 1 if and only if there is a link between node I and j. So in this case, I is 2, j is 3, there's no link. So that's why this entry here is 0. But if there would be a link, the entry is 1. For example, here in this, in row 1 and column 2, there is a 1 because the data point 1 is connected to data point 2. Okay, so that's pretty basic. Seems not too challenging and complex. So adjacency matrix. Okay, but the adjacency matrix often is not that useful. What is more useful actually is called the Laplacian, the graph or graph Laplacian matrix. Graph Laplacian. And this graph Laplacian is defined as the degree matrix. So the degree matrix is a diagonal matrix which has as its diagonal entries the number of neighbors for each node. So each node here in this empirical graph has one neighbor. That's why all the entries here are 1. So this here is the number of neighbors for node 1. This here is the number of neighbors for node 2. This here is the number of neighbors for node 3. And this here is the number of neighbors of node 4. Okay, and using this degree matrix, we can build our Laplacian matrix, which is the degree matrix minus the adjacency matrix. So if we add this together, we get then 1, minus 1, minus 1, 1. and here all zeros. 1, 1, minus 1, minus 1. So this here is the Laplacian matrix of this empirical graph. So for each empirical graph, we can determine the Laplacian matrix. So, and why now is spectral clustering called spectral clustering? Well, because we get the connected components of a graph, or we can approximate the connected components of a graph via the spectral or eigenvalue decomposition of this Laplacian matrix. So this Laplacian matrix has, you can show that each eigenvalue, any eigenvalue, lambda of L, is larger or equal than 0. And the smallest, so let's call them, we can order them. So let's start with the smallest one, the smallest. Let's denote this eigenvalue lambda 1, smaller equal than lambda 2, smaller equal than lambda 3, third largest, and smaller equal than lambda 4. Okay, and first result of graph theory or spectral graph theory, this smallest eigenvalue is equal to 0 if and only if the empirical graph is connected. Okay, so if and only if all these nodes would be connected, oh, so that's okay, that's wrong. No. This one, the second one. So the first one is always 0. The first one is always 0. So this is kind of a trivial eigenvalue. This is not really kind of interesting because this is always 0, but this here. So this here is larger than 0, strictly larger than 0, if and only if the empirical graph is connected with one component. However, in this case, we have two components. We have two clusters. Here one connected component and here one connected component. So the whole graph is not connected. We cannot move from this data point to in any way to either 3 or 4. So it's not connected. And this reflects itself in the second largest or the second eigenvalue here, lambda 2, to be equal to 0. And it turns then out that the eigenvectors, so we can compute eigenvectors. Let's call them U1, U2, that's a cool name, and U4. So these eigenvectors correspond to the eigenvalues. So for example, the first eigenvector is such that if we apply the Laplacian, then we get lambda 1 times U1. And the second one is defined by lambda 2, the second eigenvalue, equals L times U2. So, and these eigenvectors then turns out the eigenvectors corresponding to all eigenvalues that are equal to 0, and there might be more than one. So in particular, if we have two clusters, you can show, or one can show, that there are two eigenvalues when they are counted by their multiplicity. So this is a bit math detail. Don't worry if you don't understand now everything here. I just want to point out, you can read out the cluster assignments or the cluster structure from these eigenvectors, U1 and U2. In particular, you can construct by linear combining these two eigenvectors, you can construct indicators that are, so you can find a function that is equal to 1 only for the nodes in one component and equal to 0 for all other components, and vice versa. So you can construct an indicator function that is only equal to 1 for the nodes in one cluster by linearly combining these two eigenvectors. And these two eigenvectors you get from an eigenvalue decomposition, or it's also sometimes referred to as a spectral decomposition. And that's where the name spectral clustering comes from. But actually, you really don't need to worry too much about this. So I already free you from the math details. So I go back to my PowerPoint, because you don't need to implement this anymore yourself, but this is implemented in one line of Python code. And then I would like to again remind you, we will soon start the next edition of our course, Machine Learning with Python. So there you will learn how to implement all these different clustering methods that we talked about in this course in a few lines, essentially one line of Python code. Okay, but before I close this lecture, or the theory part of this lecture, I just want to point out one variation of this, or one other variant or instance of this connectivity-based clustering methods, which is very popular and called density-based clustering. So spectral clustering uses a very simple notion of connectivity. So basically, in spectral clustering, we try to find subsets of data points which are reachable by following the links. So they are reachable or connected. So this is maybe the most basic form or notion, most intuitive form of connectivity. If there is a path between two data points, they are connected. In density-based clustering, we use a slightly different notion of connectivity. This notion is based on what we refer to as core points. So a core point is a data point which is connected to a minimum number of neighbors. So within a certain distance or radius, there are at least, for example, in this case, there are at least 3 neighbors. Then it's called a core point. So these red data points are core points because they are within a given radius r or epsilon, there are 3 other data points. So it's kind of in a dense subset. That's why this method is also called density-based clustering. And the connectivity notion that DBSCAN uses then is just the connectivity as before, but 2 data points like the yellow ones here are considered connected if they can be reached by hops via only core points. So if there would be one of these paths there would be one path here, this would be a yellow point or not a red point, then C and B would be not considered as connected. They are only considered as connected because they can be reached by intermediate core points. And core points are those which have a sufficient number of nearby other data points. Okay, and this is then called, the resulting method is called DBSCAN, and it's one of the most popular. So I would say next to Kmeans and soft clustering with Gaussian mixture models and spectral clustering, maybe among the 4 or 5 most popular clustering methods. And just to contrast them, so in DBSCAN, this in its most basic implementation requires numerical features, whereas the spectral clustering just uses the empirical graph. So as soon as you can connect data points based on some domain-specific notion of similarity, you can use spectral clustering. In particular, spectral clustering doesn't require numeric data, so it also works for text. Anything you can organize as an empirical graph. DBSCAN by default requires numerical feature vectors like Kmeans and Gaussian mixture models. Another, or maybe a main difference between DBSCAN and spectral clustering is spectral clustering requires the number of clusters as an input. Like in K-means and like in Gaussian mixture models, also spectral clustering needs you to tell what is the number of clusters you're looking for. Whereas DBSCAN is a clustering method that determines automatically the number of clusters. So it also can be used to detect outliers without knowing how many clusters of regular clusters are there. So DBSCAN detects the number of clusters automatically just from the data. The difference is that in spectral clustering, we use connectivity just by the edges of a graph. Whereas in DBSCAN, the connectivity is based on intermediate nodes being core points. So if you cannot connect data points via core points, they are not connected. Even if there are intermediate data points that would allow for a path, but if these intermediate data points are not core points, so are not really well in dense areas, it doesn't count. So DBSCAN is more strict in considering data points connected. Yeah, and in DBSCAN, we use by default, we use this graph structure obtained from the Euclidean distance. So data points or nearest data points are those which have the smallest Euclidean distance. Whereas in spectral clustering, we are completely free to input an empirical graph. So this is a fully user-specified empirical graph. Whereas DBSCAN, in some sense, automatically constructs the empirical graph by looking at the Euclidean distances. Okay, and here is a very nice overview. I have just copied it from this Python documentation, this Python package called scikit-learn, which is, I would say, it's what was the calculator when I went to high school, this Texas Instruments calculator we had, a standard tool. Now this scikit-learn is almost a standard tool when you do machine learning in a high-level programming language. And as I said again, we will now have the follow-up course starting end of March, machine learning with Python, and there we will implement all these methods, these clustering methods in Python. And here you find a nice overview of different data sets. So each column here corresponds to one data set. The first column here is this 2-ring data set that I talked about in the lecture. And you see that spectral clustering and DBSCAN can cope with these ring structures, whereas Kmeans and soft clustering Gaussian mixture models fails. So it cuts these rings into pieces. Also here, some other non-Euclidean structures dealt well with spectral clustering and DBSCAN. Yeah, I highly recommend that you look up this documentation. This scikit-learn documentation is very readable, almost like a textbook. And also includes code snippets, Python code snippets, which you can copy paste and start and use it to take off for your own machine learning project. Okay, to sum up this theory part, the idea of the starting point, the launching point for connectivity-based clustering is to represent data points as an empirical graph. And in this empirical graph, we connect similar data points by edges. And the similarity notion is highly domain specific. So this can be anything, anything that allows you to tell two data points are similar or not. Then there are still different options for how to precisely define connectivity. We have seen two different notions leading to either spectral clustering or density-based clustering, DBSCAN. Both methods essentially try to find connected graph components, whereas the precise meaning of connected differs between those two methods. And these connectivity-based methods are ideal clustering methods for non-Euclidean data and cluster structure. So there was one very good question in the chat now. It seems from the figure spectral clustering and DBSCAN are suitable for any form of data set. Why do we still need K-means? That's a very good question. Well, K-means can be significantly faster in certain settings than spectral clustering. You see here the runtime for spectral clustering, for example. Here the runtime would be almost a factor 10 higher than K-means. Yeah, and on the other hand here, the cluster structure of DBSCAN for this example here might not be what you're interested in. If you really want to divide your data set into 3 clusters, then it might be beneficial to use a method that takes as input the number of clusters. So there are still reasons to use K-means clustering. A very good question. What is the reason that spectral clustering takes so long? So are there any guesses? Why do you think spectral clustering is computationally heavy or takes longer to be computed? What mathematical primitive is spectral clustering using? What matrix computation do we need to do for spectral clustering? We need to compute then. We need to compute the spectrum or spectral decomposition or eigenvalue decomposition. And computing eigenvalue decompositions is quite expensive. So it's almost as or similar expensive as inverting a matrix. And inverting a matrix that represents an empirical graph for big data, like having billions of nodes. So inverting, does any one of you know how to reliably invert a matrix of size 1 billion times 1 billion? So this is already quite challenging, and a lot of research goes into how to actually do this fast and reliable, so stable. Yeah, so the most naive methods that compute an eigenvalue decomposition, their complexity scales with the number of data points to the power of 3. So this is quite a lot of computation. And that's why you might not use spectral clustering if you have only limited computational resources, but DBSCAN might be computationally much, much lighter. Any other questions regarding connectivity-based clustering?